Antibiotic resistance in microorganisms. Antibiotic resistance in microorganisms is the ability of bacteria and other microbes to survive and multiply despite the presence of antibiotics that were previously effective against them. This resistance makes infection harder to treat, increases the duration of illness, raises medical costs, and can ultimately lead to higher mortality rates. The process of resistance typically develops through genetic mutation or the horizontal transfer of resistant genes from one bacterium to another. When antibiotics are used, especially improperly or excessively, most of the susceptible bacteria are killed, but a few may survive because they carry resistant traits. These resistant bacteria can then multiply and pass their resistant genes to others, eventually creating a population that standard antibiotics can no longer control. Bacteria can resist antibiotics through several mechanisms. They may produce enzymes that deactivate antibiotics, such as B-lactamase that destroy penicillin. They can also alter the antibiotic target sites so that the drugs no longer bind effectively. Another common strategy is using efflux pumps to expel antibiotics before they can act inside the cell. This adaptation allows bacteria to persist and thrive even in environments with high antibiotic presence. The misuse and abuse of antibiotics in human medicine, such as prescribing them for viral infection or not completing a full course, are a major contribution to this problem. Additionally, the widespread use of antibiotics in agriculture, particularly as growth promoter in livestock, accelerates the development of resistance. Poor infection control in hospital, lack of sanitation, and limited development of new antibiotics further exacerbate the issue. Several dangerous microbes have already developed resistance to multiple antibiotics. Among them are methicillin-resistant Staphylococcus aureus, vancomycin-resistant Enterococcus, extended-spectrum B-lactamase producing bacteria, carbamazepine-resistant Enterobacteria, and multivirus-resistant strain of Mycobacterium tuberculosis, Pseudomonas aeruginosa, and Acinetobacter baumannii. These organisms can cause life-threatening infections that are increasingly difficult and sometimes impossible to treat. The consequences of antibiotic resistance are profound. Patients infected with the resistant bacteria may experience prolonged illness, more severe disease, and greater risk of death. The need for more expensive and toxic treatment options leads to higher healthcare costs and longer hospital stays. Moreover, the spread of resistant bacteria can undermine the safety of routine medical procedures such as surgeries, chemotherapy, and organ transplants, all of which rely on effective antibiotics to prevent or control infection. Globally, antibiotic resistance is recognized as one of the greatest threats to public health. According to the World Health Organization, we may be approaching a post-antibiotic era where even minor infection could once again become fatal. This crisis not only affects health system but also threatens food security and global economic stability. To combat antibiotic resistance, a comprehensive and coordinated strategy is required. This includes the rational and responsible use of antibiotics in both human and animal health, improve diagnostic tools to ensure proper treatment, and strong infection prevention measures such as hand hygiene and vaccination. Hospitals must implement antibiotic stewardship programs to regulate use, while governments and private sector need to invest in the research and development of new antibiotics, alternative therapy like phage therapy, and effective vaccine. Public education is also crucial to discourage self-medication and to raise awareness about the importance of using antibiotics wisely. Furthermore, global surveillance and international cooperation are essential to monitor resistant trends and respond effectively to outbreaks.